Lastly, we're going to cover briefly a little bit on fusion. Fusion has been viewed as a panacea for the world's energy problems, and much effort and research over an extended period of time have been devoted to fusion power. A number of reactions are candidates for fusion power, usually using a combination of protium, deuterium, and tritium. Fusion has some great advantages over fission, basically of not requiring high mass number radioactive isotopes as a fuel and not yielding radioactive products. Although the individual fission of an atom of uranium-235 releases more energy than a single fusion reaction, on a mass basis, the energy release ratio is about 7:1. So at the bottom of the slide, you can see here a little chart which looks at fuel consumption for various power plants. So if we have, for example, a coal power plant that consumes 4.4 times 10 to the 6 metric tons of black coal, that equivalent for brown coal would be 10.8 times 10 to the 6 metric tons. In fission, that equivalent energy would be done by 1.3 metric tons of uranium-235. And in fusion, that equivalent energy would be the consumption of 150 kilograms of deuterium and 500 kilograms of lithium. So the question that usually comes up is, why hasn't fusion been realized? Well, the requirements for fusion are very difficult to attain and sustain. Any of the fusion reactions listed in the prior slide requires the individual fuel nuclei to come together and then fuse. But all nuclei have positive charges, thus the nuclei will repel each other unless the kinetic energy of each nucleus is sufficient to overcome the Coulomb repulsive force. For fusion to occur, the speed of each nucleus must be very high, and very high kinetic energies correspond to very high temperature. The resulting temperatures is in the range of 10 to 300 times 10 to the 6 Kelvin. At these elevated temperatures, the reactants are ionized, with all electrons stripped from their orbits about the nucleus, and a plasma results. The plasma consists of electrons and a positively charged nuclei. The basic problems for a fusion reactor are threefold. One is how to generate the high temperatures required. That's basically been solved. The other two that are still in progress is how to contain the hot plasma and how to achieve the required density of the plasma so that fusion takes place. So the plasma, how do you contain it? There's different ways of different theories out there. There's, for example, magnetic containment or inertial containment. Since 1970, this chart covers up through 2000. You can see the progress in fusion energy in terms of watt seconds, achieving close to or a little over 10,000 watt seconds worth of fusion up to the year 2000 or close to the year 2000. So how will a fission reactor look like? You basically have here a containment in the toroidal axis, or the toroidal axes, with all of the necessary components to keep that reaction going. Again, the big issue being one of the big issues being containment. This is a cutout example of what we call the GET, which is the largest tokamak in operation, tokamak being a fusion reactor. And it has been known as the world's foremost machine for 20 years in studying fusion. In 1997, this particular reactor produced a peak power of 16 megawatts, with 10 megawatts being sustained for over a half a second, which is basically the current status or how far we've come with the production of energy by fusion. Thank you very much. This slide ends our chapter on nuclear power.